So up to now we have examined second step calculation of k parameters for the real roots. For the complex roots, what is left is the multiple roots. When the characteristic roots are multiple roots, then how are we going to calculate the k parameters? That's the question now. So we are examining this k parameter calculation for the physical solutions, that means natural and forced solutions. So we are going to examine them separately. First one is the natural solution. So that is the mathematical model of the circuit we are dealing with. That means parallel RLC circuit which is delivered by an independent current source. So the homogeneous part of it is this. We got the characteristic roots. Discriminant is equal to 0. Then the characteristic roots are multiple roots. So homogeneous solution is going to be like that. This homogeneous solution is the same as the natural solution. Why is that? Because in the homogeneous solution we consider the independent sources as 0. In the natural solution we consider the independent zeros deactivated or removed from the circuit, and the only energy sources are the initial conditions related energy sources, that is stored energy. That's stored. So the difference between this solution, although it's that homogeneous solution, in this case it is natural solution. The only difference between homogeneous solution and the natural solution is this. In the homogeneous solution, we do calculate these k values after we add the particular solution here with the given initial conditions. Now in here, since there is no independent source, we don't have any particular solution. This solution is the natural solution. In this natural solution, I will be calculating these k values for the given initial conditions, not after the calculation of the particular solution. That's the only difference. So how are we going to find all that? So this is the numerical values. So if we choose these numerical values, we're going to find these multiple roots, and our numerical differential equation is going to be this one, which represent our circuit. This circuit do not include independent current source in it. So the second step of calculation of these k values, how we are going to calculate it? We need initial condition plus the initial condition related state variables derivatives initial conditions. We already said how to calculate these initial conditions from the given mathematical model, isn't it? That is the mathematical model. If we replace t with 0 here, these are going to be the initial conditions. These are going to be the state variables, the derivatives initial conditions. So it is done here. So these are the initial conditions. So state variables, derivatives initial conditions are given here. So here you are, our natural solution is this. We are trying to calculate these k values. For the VCT, that means capacitor voltage, we've got two parameters to be calculated. These are K11 and K12. So our estimation is going to be, since the characteristic roots are multiple roots, our estimation is going to be, the first one is e to the power s1t. S1 is equal to st. That's why the second term includes t times e to the power minus s1t. So if you replace t with 0 in the first equation, we're going to have one equation here. Since the initial condition is 0, 0 times k1 into power minus 10,000 T, that gives you 1. And this time when T replaced with 0, this is going to be 0, so K11 becomes equal to 0. So if we take the derivative of the function, so derivative of the function and replace T with 0, so that is the state variable's derivative's initial condition that we have already found here, and take the differential of this function, you're going to end up with this one. If you replace T with 0, you're going to end up with this K12. So this this equation and this equation, two unknowns, two equations, we end up with this K12 is equal to this one. So we see T natural, our state variable. Solution is this. So if we did similar things for the inductor currents, we are going to find the inductor current as it is here. So the drawing is this. So we can check now whether this is a natural solution or not. There are some critiques that we could do for that. For example, we could see that our initial conditions for the capacitor is 0, so it is given here, 0 here, and our function starts from this 0 case. And after a while, this function becomes 0. This is an expected result. Why is that? Because these are related with the limited energy stored on the capacitors and inductors. So when this energy absorbed by the resistor in the circuit, so that energy finishes. Energy finishes means current and voltages become 0. If you apply a continuous energy source like an independent current source, then you are pumping energy, delivering energy to your circuit, so you're going to observe a continuous function changing with time. In this case, when the energy disappears, so that means all the currents and voltages become 0, so that is the expected result here. Another thing that we've got to pay attention here, our voltage jumps over 1400 volts. But this is for a very short time. Why is that? This is 2 milliseconds. So this is in the range of 20 microseconds. So very short time, we've got a high voltage on our capacitor. What does this mean? Maybe we are over the limits of the capacitor. If we are over the limit, maybe the capacitor burns, or it won't be capacitor anymore. In this case, this burning is not related to the circuit unstable or stable. It is directly related with the limits of the capacitor. So these limits should be given by the manufacturer to us. So if we are over the capacitor limit, so you've got to change the capacitor with another capacitor which could face these limits. That means do not burn when the voltage between its terminals over 1400. So look at the second one. So since this is a natural solution, the function starts from the initial conditions, and this one also goes to 0. That's the expected result, because the energy is a limited amount of energy stored in the circuit, so this energy is going to disappear after a while. So the second part of our solution is the forced solution. So we examined the natural solution. Now we will be examining the forced solution. In the forced solution, initial conditions are going to be considered as 0. That means no energy stored on the state elements, and independent source is in the circle. So in this case, our mathematical model is this. This is the parametric one, and this one, this mathematical, this is the characteristic equation, characteristic roots. If the discriminant is equal to 0, it's going to be equal, characteristic roots equal to this one, and these are the multiple roots. In this case, that's the homogeneous solution. There should be added a particular solution to this one. So we're going to see it here. Here you are. If you choose these element values, after the calculation of the characteristic roots, we end up with the multiple roots, and parametric solution is this, parametric mathematical model is this one, and this is the numerical one. So our homogeneous solution is this one, and since the independent source is independent DC current source, we can calculate the particular solution. That's the particular solution, and those two up. So that is the forced solution. Forced solution has got homogeneous part and the particular part. The difference for the forced solution is going to be this. We will be using the initial conditions equal to 0 while we are calculating these k values. So we will see it now here. So our the forced solution has got that format because of the multiple roots, and the first variable, state variable, is VCT. If you replace t with 0, we are going to get one equation. We are going to take the derivative of the first state variable here, and then replace t with 0, get the derivatives initial conditions. We have calculated this by using this, isn't it? If you replace t with 0, you can find the derivatives initial conditions while the VC and IL is equal to 0. This is the forced solution, therefore the initial conditions are 0, so this term becomes 0, but derivatives initial conditions could be any value including the 0. So it doesn't mean that initial conditions 0 means initial conditions related state variables derivatives initial conditions are 0. We can't say that. So in here what we have done, we found the first equation and then get the derivative of the VCT function and replace t with the 0. We get another equation. Solution of those two equations gives us the K1 and K1 Conclusion is this. If we do the similar things for the inductor currents, we are going to end up with this function. So graphs are going to be like that. So when you see these graphs, the initial conditions are 0, you can easily see that. So it starts from the 0 point, this one also starts from the 0 point. Since this is a forced solution, that means it includes the independent source in it. Because of the independent source, and this independent source is DC source, there is going to be a particular DC solution that is seen in the current here. Therefore, this element current does not go to 0 value, it goes a constant value, that is 1. That's particular solution. Continuously we are going to examine this particular solution here. This is going to be the transient solution. So in this case, for the VCT, it becomes 0. Why it becomes 0? Because our solution has no, our particular solution is 0, isn't it? Since the particular solution is 0, that function became 0. This is just a coincidence. So the next thing is, after finding the natural solution in here and the forced solution in here, when you add those up, we are going to find the general solution. natural solution and the forced solution. When you add those up, we are going to get the mathematical solution that we already found, which includes homogeneous solution and the particular solution. So addition of those two gives me that result. You can check it. So that's the end of this chapter and also end of this frame video.